I'll assume that I can start off with the easy problems versus the hard problem versus the real problem of consciousness. So, if anyone remembers from past weeks, I've been referring to the easy and hard problems as coined by David Chalmers, right? So the easy problems, are the study of how do cognitions occur, like what are the brain processes accounting for them, how does the brain process information, these kinds of objective, very objective questions. The hard problem is bridging the gap from how does objective information processing become a subjective phenomena? How do you get objective patterns of neural activity resulting in seemingly immaterial and subjective experience or consciousness? And Seth kind of points out a third option here, and he says, well, I'm not going to try to account for why is it that a neural system produces this thing, but rather he investigates what he calls the real problem of consciousness, or at least what we can target for now, which is the neural correlates of consciousness. What are the biological mechanisms accounting for consciousness? Um, and so he says, okay, in order to study this, we can target consciousness in three levels. Um, so the first classification of consciousness is just level, right? The level of consciousness, is the property of being conscious at all, or how conscious, right? And then there's content, which is what are the specific things that consciousness is about, right? Is it about pain? Is it about uh, auditory stimuli? Is it about a certain kind of red? Are you looking at sweaters? Are you reading a book? Is it deep in thought? Whatever. It's all of these different contents, right? These little specifics. And then the third classification he finds important is the sense of self, right? So the conscious experiences belonging to the self and the sense of identity and sort of carrying those conscious experiences throughout time to form one conscious identity. Um, he talks about how we have different states of consciousness across wakefulness and sleeps, right? So we can have across the sleep cycle varying degrees of consciousness, right? Where you have deep sleep being the least conscious, you have light sleep to being the a little bit more conscious, but not very conscious. And then you have dreaming REM sleep, and you have wakefulness and whatever as being more and more conscious. He also talks about like clinical disorders where you have consciousness, for example, in the vegetative state, you don't have consciousness, but he suggests locked-in syndrome, which is where someone loses all motor functions because of whatever brain pathology. They lose all motor functions, so they can't move, but they can maybe blink or move their eyes, maybe, right? So for all intents and purposes, they're extremely paralyzed. And sometimes you ask, well, if they lose all motor functions entirely, do you know if they're conscious, right? Like, what if they can't blink or move their eyes? Um, and you can use brain imaging to basically ask these people to do certain things, which you'll see this in the introductory psychology book. Siddharth, Gazzaniga cites a study where they ask this person to think of certain things, and then they look at the brain activity, and then they can associate that brain activity with normal thought of those things, or just a response pattern, and then they realize that this person is responding with their brain, but they have no motor abilities to respond behaviorally, right? So anyways, he's got these three classifications of consciousness: level, content, and self. And so of course he poses the question, so what exactly makes us conscious? Is it the number of neurons? Well, he cites that no, like you can take out 80 billion neurons, you can take out billions and billions of neurons, it doesn't seem to affect consciousness. In fact, the cerebellum, where about a large majority of your neurons exist, is definitely not the source of consciousness, because you can take that thing out and people seem consciously fine. Is it specific regions? Well, he cites like the reticular activating system, which I talked about last week with Mark Solms. He says that this is not a source of consciousness, but rather this is more like a power plug to the brain and consciousness. So he suggests it's not really specific regions. It's not the number of neurons per se. Is it simple neural activity? Is just activity itself an indication of consciousness? Well, not exactly, right? Because in non-conscious sleep, right, so deep sleep, you have brain activity, right? In fact, you can have some brain activity a little bit after death or whatever, right? Is this consciousness? Probably not, right? He suggests instead the information integration theory helps answer this question. It's about it's about this sort of bidirectional causal power. It's about parts of the brain influencing one another, right? It's about the manifestation of certain states out of other states as influenced by other neurons. In other words, he suggests that consciousness is an integration of information, right? And so information being one state expressed out of many potential states, that's information. And the integration means that, okay, these states are then interdependent on one another. So for example, in consciousness, you can see a shape, right? And the shape necessarily has a color. It has some sort of light associated with it, as well as the shape itself. To see those colors radiating from the shape, that's dependent on the shape itself, right? But the colors will allow you to see the shape, right? So you can't see the shape if it doesn't interact with light in a meaningful way, right? If it's invisible. But whatever light you see is going to take on that shape, and so now you have an integration of color and shape, right? As one example out of many potentials, right? So consciousness is an integration of information, and similarly, the brain. He cites that you can have. He cites a sort of canonistic study of you take a TMS. It's basically like you pump a current into the brain, right? And what you see is that people who are unconscious, for example, in a vegetative state, and across all of these different states of sleep and wakefulness and whatever, as consciousness increases, what you find is you have a higher what's called perturbation index, meaning that whatever current you pump into the area of the cortex, the response is going to be more spatially, temporally complex, meaning the response is going to be longer and it's going to be more varied. So basically, the assumption here then is that the neurons themselves are more connected and they have more influence on one another. So the objective information here then is, an increase in integration of these potential states. So the different excitation of the neurons or whatever are going to be influenced by other neurons, and you're going to create a varied and longer, more robust response. Whereas if you have less consciousness, the stimulation kind of hits the area. It doesn't become very dynamic, and it doesn't last as long. So the idea is that, okay, then these connections it's less connected, and the connections are less meaningful. So it doesn't influence other regions in a meaningful way. And so this is a great way of explaining the level of consciousness, right? And again, if anyone remembers from the integration information theory I talked about in the very first talk, it's simply a quantification of the level of consciousness. And he cites that there are real neurological clinics today in the UK using the perturbation index or other forms of neuroimaging to gauge how conscious is, for example, a vegetative patient. Are they making improvements, right? And this is an important question if you want to, gauge the choice of should we unplug this patient, right? If they're not conscious, if they don't seem to be improving ever, they're kind of dead, right? They're nearly dead in any meaningful way. Okay. So. Sorry, I'm just looking at my notes. He also cites that if you look at just spontaneous activity, so this is just the activity that just occurs, maybe irrespective of external stimuli. So you kind of just have this, for example, if anyone's ever heard of mind wandering, right? This is just this kind of spontaneous thought that we go through where we think of ourselves in different situations, or maybe we just think of different things and we just kind of get immersed in thought, and consciousness becomes a little bit less dependent on external stimuli. Well, in this kind of spontaneous activity, what he finds is that it's the same thing as if you were to induce an electric current into the brain. What you find is that the spontaneous activity itself, as consciousness increases, also becomes more complex, spatially, temporally, more varied, more robust. He compares those in mild sedation to waking to general anesthesia. Again, the same pattern here. Wakeful rest, interestingly, so you being awake is comparable to REM sleep, which is the dreaming stage of sleep. So In this regard, he's saying that potentially your dreaming state is a similar level of consciousness to just regular wakefulness. However, other stages are not the same case as would be expected. Um, and he also notes that there's increasing complexity in the frontal regions of the brain. So maybe suggesting that the frontal regions of the brain are more important for creating the contents of consciousness. Interestingly, he also cites a similar um, line of research in psychedelics. So after you give someone a psychedelic, the pattern of responding becomes more varied, more spatially, temporally complex. Um, you know, maybe hinting at an increased level of consciousness. Um, so yes, and he asks, so who cares, right? Like, who cares if we're measuring the level of consciousness? Like, what's the big whoop? And he suggests, well, this is actually an important step in studying anything, right? And he cites the study of heat and thermodynamics, and he says once we were able to measure heat and know what it was, we could then turn it into a whole meaningful discipline, and now we can talk about um, thermodynamics in a way that's meaningful beyond human experience. We can talk about thermodynamics in the sun. We can talk about absolute freezing and all of these principles of science without having to directly experience it, and we can understand it in a deeper way. And so he suggests, in quantifying consciousness, we can do a similar approach to studying it. Okay. Okay. So then he now gauges the second classification of consciousness, the contents. And he cites Helmholtz, who was a scientist, German scientist in the 1800s, as being the first to propose the brain as a prediction machine. And um, so he talks about perception as being our best guess of interpreting meaning out of ambiguous stimuli, right? Um, he says that brain activity is highly unrelated to physical patterns of stimuli in the real world or outside of the brain, and he says that the only way that we can make sense out of these incredibly ambiguous patterns of information is by using Bayesian inference, which I talked about maybe a week or two ago in the other talk. Um, anyways. He talks about optical illusions, right? So importantly, optical illusions help us understand, well, what are the biases in our perceptual processing, right? And he cites a famous optical illusion. If anyone's ever seen this, it's like a checkered board with a cylinder on the board, right? And the cylinder casts a shadow on the board. And what happens is that you perceive the white checker to now the white checker in the shadow seems to be lighter than the dark checkers outside of the shadow. But once you remove the shadow from the image, you realize that what you thought were white checkers within the shadow are actually the same gray color as the whites outside of the shadow. Um, and and or sorry, the white in the shadow is the same color as the black tiles outside of the shadow. And his point here is that, well, the brain isn't a good photoreceptor. It's not a good measure of the properties of light. Rather, it's a good machine for processing patterns of relations and imposing meaning on them, so that way it can operate within the world in a sensible way. Um, so yes, he cites that as um, one one illusion to cite that the brain is a predictive machine, and he shows a graph where you have basically a normal distribution of prior beliefs, right, and then you have actual sensory data, and then you have perception being a combination of those two, where you basically have this interaction between prior beliefs or prior system experiences or learning and current sensory data. In other words, what you have is a perception as this place in the middle between bottom-up processing, right? So the current sensory stimulation on the retina, and then moving upward through the visual pathway to more complex areas of processing, So you have this processing occurring, and at the same time, you have a reverse, feedback propagating down through the system, right? So you can think of it as two directions through a hierarchy of processing. Moise, you may think just very much like a normal neural network where you have bidirectional influence, right, going both ways through the network. And he suggests that this is ultimately very key in determining how do we perceive audition, how do we perceive anything, right? How do we perceive sight, anything? He calls it actually a controlled hallucination. He says this is essentially a controlled hallucination, and a hallucination, or any malfunctions in perception is an uncontrolled hallucination. So he cites that our understanding of this sort of bias in processing allows us to pull off things like MVPA, where we take patterns of responding to sensory stimuli, and we can actually infer what is the brain looking at without actually having to look at what the brain is looking at. He also cites another approach called using Granger causality, sensitive to information flow. These researchers, Bastos et al., 2015, they find that bottom-up and top-down processing are conveying information at different frequencies as predicted. Okay. So, interestingly, a very insightful or very good portrayal of what the significance of this top-down processing and allowing you to consciously perceive. So, in other ways, whatever beliefs or prior experiences you have to allow you to bias and then interpret ambiguous information, he suggests that, okay, if you use TMS to inhibit top-down regions of the cortex, you can actually totally interfere with bottom-up information processing, right? And so he cites a study by, I don't think I can pronounce that name, but he cites a study where they use optogenetics, which is a form of, you create these little bioluminescent channels within just like normal membranes. You can do it in mammals. And in doing this, you can flash a light on it, and this activates or deactivates depending on how you manipulate it. But in any case, you use the optogenetics to manipulate a network's activity. And he says, okay, so you use the optogenetics, as these researchers did, and they turned off a very high order processing area, and it totally destroyed the ability for the mice to discriminate a tactile stimuli. So they couldn't perceive it correctly anymore, essentially, because they turned off higher order processing regions. And so now the mice could feel it with their hands, but they couldn't actually perceive it correctly, or at least at the same, not nearly at the same proficiency as they would otherwise. And so he suggests again that the processing perception, or how the brain processes, is bidirectional. It's not just bottom up from retina or simple sensory organs in the skin or whatever to simple processing regions in the brain to more complex, but rather it goes both ways. And he suggests that this is the mechanism we need to study for explaining how is it that the brain produces consciousness. So he's not answering the deep why here of the hard problem, maybe evolution, or how does the neuron produce a seemingly immaterial experience, but he's rather justifying the neural correlates of consciousness approach, where we're just studying, what brain regions are sufficient for consciousness, what are the dynamics of these brain regions in explaining, or, as they correlate with conscious contents and experience and whatever. So he studies, or he cites Pascal, Leon, and Walsh, who show a strong connection between top-down and bottom-up consciousness through the aforementioned approach of TMS, optogenetic inhibition. Actually, in this case, Pascal and Leon, they use TMS to inhibit top-down regions of processing for visual information. And this so without blinding someone in their eyeballs, right, in simple regions of visual processing, they go to higher order brain regions. They inhibit them, and then although the person is seeing the stimuli, they can no longer actually detect it or accurately report what they're seeing. So for all intents and purposes, they're blind to the stimuli being shown to them, right? And so again, he's showing it's like, okay, so we have manipulation of the brain's ability to predict what it's seeing, right? Because you're getting top-down processing unimpaired, right? So the eyes are still taking in their input of visual information, they're sending it up visual pathways, but nothing's being sent back down the pathway with the prior belief or biases in allowing the bottom-up approach to efficiently process the data. Um, so he asks, Seth, do we consciously see then what we expect? Or do we rather see violations of expectations? Do we see what matches what we believe we're seeing? Or do we see things that we weren't expecting to see, or things which seem impossible? And he cites continuous flash suppression, which I think I've mentioned every week as a paradigm, where you take two goggles, right? And in one goggle, you put random patterns of stimulation, random visual stimuli. And in the other, you put some meaningful stimuli. And so, his student, he puts in a face or a house in the other goggle, right? And he just flashes it, right? And so what would you expect to see? What you would expect verbally, right? Like you would say before you go into this thing, you would say, "Oh yeah, I would obviously see if someone flashed a face into one of my eyeballs. I would obviously see if someone flashed a house into one of my eyeballs." But rather, this isn't the case, or at least what you see is dependent on what you expect to see. And so, what he manipulates here is whether or not you see a face or a house. And then the second manipulation is, what do the experimenters tell you you will see flash in one of your retinas? And so if you tell people, okay, I'm going to flash a house in front of, the goggle, one of the goggles, what you find is that the person is actually less likely to see if you flash a face, and they're less likely to see what it was. So basically, it's important to note here that if you flash a stimuli in front of someone, maybe you think of a quick burst of something you see. You don't really know what it is. You need to be able to see it long enough to process what it is, right? And so if you give them a quick flash, they're they're able to detect what it is meaningfully and identify what it is if you first tell them what they're going to see. But if you don't tell them, they're less likely to know what it is, less likely to even detect something being present. And then moreover, if you tell them they're going to see something else, they're even less likely to appropriately identify it. They might be about as likely as detecting it because they'll be expecting something, but they're not going to identify it correctly, or at least they're less likely to. Um, Okay, so basically the key insight here is that what you tell someone to expect, whatever their top-down expectations of what they're going to see is going to influence what they actually perceive, what they detect, and how accurately they detect it. He also cites motion-induced blindness as a paradigm. So you take a dot in the middle of sensory stimuli and you fixate on that dot. And then what he does is he spins a grid around that dot, right? And in your periphery, there's going to be a dot, another dot that doesn't move. And what's going to happen is you become blind to that. And for me, I become blind in about like a second or two. Like it's very quick. But then once you just stop fixating on the point in the middle of the rotating grid, you notice that the dot's still there and it's always been there and nothing's changed. And so it's really amazing to mess with your visual processing in this way. But what he does here is he further manipulates the study, and he says, okay, if we tell so you change the color of the dot in the periphery, and what he says is if we tell them what we're going to change the color to, they're more likely to see the change in the dot color, and they're more likely to see it faster, right? So if I don't tell you it's going to change color, you're less likely to even consciously see it. But the amazing thing here, remember, is that all of these things, nothing changes in your retinal input. Nothing changes in bottom-up processing, only top-down expectations of what is it you're going to see. And then this totally alters the conscious perception as an end outcome. Okay. Um, okay. And then his next line of research, he cites the alpha wave. Okay. So he cites that the alpha wave is another important neurological correlate of consciousness, such that so it's basically a wave of processing. So basically, you think of populations of neurons firing. If anyone's familiar with an EEG, this is what I'm referencing. Just you're recording waves of neural firing. So this is just populations, right? You're basically detecting what is the main amount of firing at a given time, right? And so you're measuring large populations of neural firing. And what you find is that in the visual system, they're processing it in an alpha wave. So this is about, like 10 cycles per second. So like 10 fires per second at a large population level is what you're finding. 10 peaks in firing from the population of neurons in the visual cortex. And he suggests that at the peak of the alpha wave, what you find is that you have the most influence from people's expectations, right? So if you try uh, these experiments where you do manipulation of people's expectations, for example, he shows people a very um, like low resolution, hard to see pattern of lines, right? They're very hard to see. Um, or they're hard to see, but you can see them. So he flashes these lines. They're just not very bright lines, and they're hard to see. Um, and if he tells you he's going to flash these lines, you actually detecting these lines is going to be dependent on the alpha wave. So what he finds is if he flashes the stimuli at the peak of someone's alpha wave, they're most likely to see it if you tell them they will see the lines, right? But he says in the trough or the low point of the alpha wave, what you find is that um, people are more likely to actually detect bottom-up processing, right? So they're more likely to just detect the lines regardless of what you say and what expectations you put in them, but rather they see the lines of stimuli based on bottom-up processing and whatever the retina sees. Okay. Uh, okay. Sorry. Okay. Another line of research he cites is with visual reality or virtual reality. Um, so he uses virtual reality to whatever mess with people's perception and study perception, and so one of the things he does is he studies perceptual presence. This is we perceive an object, and do we actually perceive it as being there, as being a real object? And so this is an inconclusive line of his work, um, but so basically, he takes objects in virtual reality, and he allows you to one manipulate it as you would in a real life object. So as you move it, it reliably. Here, I'm just going to turn on my video. As you move the object, right, it reliably moves with your VR, and you can see all of the different parts, right? But he says if you kind of in the virtual reality manipulate it so it's just a fixed point, and it doesn't matter how you move yourself or how you try to move the object, all you see is the photo, you might not get the same perception as you know um, a full dimensional object. um, Anyways, and I guess the important insight here with this study of this almost like 3D perception of an object or whatever is that the brain has expectations of what is it going to see, right? So rather than me like looking at this object, right, and I'm interpreting concurrent visual stimuli, and I'm only processing what is here. He says that my brain is also processing what's on the other side of this. So I can have an idea of what's on the back side of this before I've even seen it. And then as I move the object towards myself and I see the whole thing, it's like, okay, yes, I'm confirming, or maybe I'm not confirming what I previously thought about the object. But as I'm confirming whatever I thought, it allows me to process it more quickly and more accurately. Okay. Um, Anyways, his ultimate question here is sorry. Yeah. Anyways, his ultimate question here is how do we, perceive and conceive of these objects in 3D space? To me, what's amazing about this idea of getting like a full prediction of the object without even seeing the full thing is that like what's amazing to me is that almost seems like an infinite computation. Like how can you possibly get a concept of this thing in 3D without seeing the full thing, right? Because you know an object can be represented in an infinite number of like patterns of data, right? From different orientations, from different distances from the retina, right? And so this would change the data structure, but it wouldn't change the relationships within it. And so there's just something to me that's amazing about, getting a three-dimensional conception of the thing before even seeing it, at least in all dimensions. There's something amazing about that to me. Okay. He does another set of experiments with virtual reality where he uses something called Google Deep Dream algorithm to create what he calls overactive priors. And I guess maybe Moise would know more about this, but it's something like you create extreme bias in the neural network such that at like sort of the endpoint of the neural network, it's expecting to see what he put in as dog, right? So it's expecting to see dogs or an image of dogs or whatever. And then you have actual input. And as the input moves through the neural network, right, this thing is then propagating back, and it's imposing dog, and it's allowing you to see dog in places that you don't actually see dogs. And so it's hard to explain, but as you wear the virtual reality, the AI is, or as they record a scene, the AI is, well, okay, later, Sebastian. So as you look around the visual scene, what you see is a bunch of hallucinations. Um, and this is comparable to what we experience. It's called pareidolia. And so pareidolia is, you look at the clouds and you see a face. You look at a pattern of stains in the wall and you see a face. What is this? This is extreme bias towards seeing faces in patterns of sensory information are extreme bias. This duck bias is the same thing where the system is expecting to see dogs, and it's so biased towards seeing dogs that it sees dogs. And us, from an evolutionary perspective, faces are very important patterns of information, right? Like social creatures are very, very important creatures in our environment. In fact, there's a line of research from social psychology called social facilitation, right, which studies the physiological hyperactivity we experience in the presence of others, right? Just the mere presence of them can allow us to perform better on simple tasks. Um, for example, in studies of social facilitation, what you will find is even cockroaches can perform better on a simple maze if other cockroaches are watching it. So if it just knows that other cockroaches are staring from a distance, it will perform better on the maze. However, this is only true of simple mazes, not complex ones. And the idea is that you get this physiological arousal from being the presence of social others, right? Because social others are very important, right? And so you perform better on simple tasks just because of the increased physiological arousal, right? But on complex ones, it creates nervousness and you don't do as well, as is supported in human research and as well as the cockroaches who perform worse on complex tasks. Okay. I'm almost done. Thank you guys for listening. Okay, so he ultimately says that the content of consciousness, right, like what we see, right, you can inhibit it from a top-down perspective by manipulating top-down regions of cortex, right, and so then as you only get bottom-up processing, but if you inhibit the top-down, you don't see what is there, right? If you influence the top-down by telling someone what to expect, then they're more likely to see it, even though the bottom-up processing hasn't changed. So he says top-down processing is ultimately very important. And he says that the content of consciousness is therefore a prediction. He says you're ultimately predicting what you're going to see, and perception is so dependent on predictions that consciousness itself is a product of this neural prediction of what is it you're going to see, right? So and that's influenced by what you're currently seeing. So the bottom-up processing influences the top-down, and the top-down influences the bottom-up, and you get a bidirectional processing here. Okay. Um, he quotes an artist here. Perception is largely an active process of imagination um, by the perceiver. Okay, and then there's the last uh, conception of consciousness, which is the consciousness of self, right? So you have the perception that you have your body, right, and you have your experiences across time and whatever. He distinguishes these self perceptions or self consciousness into the bodily self, which is your perception of the body belonging to you, and the information that happens to it, happening to it and not other things. This may sound very abstract, but you also have the perception of your body in space. To elucidate what is meant by this, maybe there's a couple of clinical cases. 90. Does anyone know what phantom limb pain is? It happens to 95% of people who lose an arm, a finger, a leg. Phantom limb is this perception that you have something, you have a limb there that's not actually there. Amazingly, it's sorry. The phantom limb tells us a lot about the expectations we have about our own body, right? That allows us to interpret the bottom-up information relevant to that part of the body, right? So yes, 95% of people, as they lose a limb, they still feel it being there. They feel it very vividly, often in pain. Leads a lot of people to committing suicide because of the pain. It's very hard to treat, whatever. There's other work by, I think it's Ronald Meltzoff, maybe. Melzack, sorry. Ronald Melzack, who he creates phantom limbs in healthy people, right? So I can create a phantom arm in you if I put in an anesthetic, a local anesthetic to your arm, so you can't feel anything in the brachial plexus. So there's nothing, no sensory information going to the spinal cord. So for all purposes, like you have nothing coming in from this arm. So your brain, it has no information of the arm, but yet you'll experience a phantom limb. It's very amazing. People with an arm here will experience a fake limb basically coming out of thin air. They experience it as a very real thing. They don't necessarily see it, but they can feel it and they can locate it. If you don't look at it, they can point to where it is, right? And they can say, I feel the limb very vividly. It's often right here, right? So this is the idea of where is the bias? What is the model we have for ourselves? The model involves at least the arms being here or here. I believe here most of the time, though. Anyways, so this is all related to the sense of the body, the body self, right? Okay, and then he has the perspectival self, right, which he talks about as this consciousness where we like everything we perceive, we are perceiving. No one else is perceiving it, just us, right? You're not perceiving the perceptions of others, right? So you don't ever see what anyone else sees exactly, and you know that, right? You know that at any given point in space and time, you never see what anyone else sees. You never experience what anyone else experiences, right? It's your perception. He talks about the volitional self, right? So the perception that we have free will of ourselves. This is a form of consciousness. The narrative self. So this is refers to as the autobiographical, right? So this is all of our episodic memories. So all of our memories of our life that we actually remember as these sort of like episodes or videos in our head. This is part of autobiographical or narrative self. And furthermore, there's the semantic information to do with the narrative, right, where you memorize facts about yourself, but not necessarily anything episodic. And then lastly, there's the social self. So we have a perception of ourself within society as another form of consciousness. Okay, what he studies primarily is the sense of body, the sense of body self, right? Another way of highlighting like the clinical interest in the body self is very, very interesting. There's another condition called body integrity dysmorphia. It's compared as the opposite of phantom limb, and it's this perception that people have that like this arm I have isn't mine. I remember reading for the mechanisms of pain class. We read a story of a patient who would wake up screaming in the middle of the night, just freaked out. Convinced that the medical staff had played a trick on him, that they put a dead leg in his bed or they attached it to him. And so what this patient would do every night is he would wake up, he would feel like this leg, and it wouldn't feel like his. So he would touch it, and it wouldn't feel like his. He would see it, it wouldn't feel like his. It wouldn't resonate as something that's his. Perhaps this is due to pathology in the insula, I believe, if anyone's interested. But anyways, so he has this perception that this leg is not mine. And this sounds crazy, and these people feel crazy because they're not psychotic by any means. Like, you can talk to them about anything, they seem fairly normal, right? With the exception of this. They feel like the thing is not theirs, and they often get it cut off. It causes them such distress to feel like they have a dead limb hanging from them. So there's one patient, he would throw the leg out of the bed, and of course he would go with it, and then he'd be very upset because he thought that the nurses would sneak in at night and attach a dead leg to him because he was just convinced no way was it his. But again, this is a pathology in the consciousness of body self. Okay. And he's so Seth is ultimately claiming that our perception of the body self, similarly to just normal perception of the exteroceptive world, he suggests that the interoceptive, right, the sense of self as a body, is ultimately, again, a best guess. It's a predictive model. It's a consciousness which results from this prediction. He tries to argue in favor of this whole body sense of self thing as a result of just bodily processing and necessary processing to maintain, healthy body physiology and understanding where it is and allowing it to operate in space, right? He's the James Lange theory of emotion. It's just a theory that's been long thrown in the trash, but anyways, he does cite it, and he says, okay, can anyone? So you would imagine, right? Here's the James Lange theory of emotion. You see a bear, right? Or you see a scary stimuli, or you see something which causes emotion. The famous example is a bear. You see the bear, right? What makes you afraid? Where does the emotion come from? William James and his component, or his counterpart Lange, they suggested that, well, it's actually not the bear that makes your mind afraid. What it actually is the physiological arousal from unconscious parts of the brain. They process the process the bear being present, and then they create a fight or flight response, and then higher order processing areas in the brain interpret this physiological arousal as meaning that you are afraid. Again, I find it really odd that Seth cites the James Lange theory of emotion as this sort of like evidence for whatever, as a line of logic to his bodily self neuroscience. But and the reason it's odd that he cites this theory is just because, yes, your interpretation of your physiological arousal is important, but what's actually the case is that your physiological states are very similar, right? So anytime you're physiologically aroused, they're usually very, very similar to other states, right? So feeling sexually aroused is similar to feeling angry, is similar to feeling very happy. Like, you get this vasodilation, you get this increased heart rate. Like, things are pretty similar, right? The more contemporary theory is that both are important, right? So there is the processing of the physiological arousal, which is important, and there's the processing of the external world. A very interesting study that comes to mind for me is a very famous one. You can manipulate how angry or happy people are based on what is going on around them. So in a famous study, what you have is this what is called a confederate, which is an actor in a psychological study. So he's a fake actor, and then you have a real participant, so some college kid. What you do is you invite the college kid in, right? And you either inject into him this solution, and you have to lie. So you tell him, okay, this is, you might tell him it's saline, right? Or you might tell him, it's going to make you, I don't know, it'll give you energy. Like, it's like caffeine, right? So you tell him something like this, right? Okay, whatever. And if you give him saline, it doesn't really matter what's happening around him. He doesn't really get as aroused. If you give him adrenaline, right? Enough adrenaline to arouse him, he's already aroused, right? And then you make the confederate become agitated, right? So you make the actor become agitated. He's going to see the actor becoming agitated, and now he himself will actually become more agitated, right? Especially if the Confederate encourages him. So if the Confederate just starts getting agitated about something happening, this guy, the actual participant, will also is more likely to become more agitated with him. However, if the Confederate becomes euphoric, just happy about something happening, whatever that experimental stimuli is, whatever it is, if the Confederate is acting more happy, then the participant also becomes more happy, and it's an interpretation of the physiological arousal, not and so it's both an interpretation of the physiological arousal and the external stimuli. In any case, there's this important, top-down, bottom-up processing, right, where you have, and an integration, right, where you're processing external information, internal information in the body, very basic stuff, and you're trying to make sense of how those two things relate, and then you develop an emotion. Okay. Some more work in his line of the body self. The rubber hand illusion. If anyone's ever familiar with this, it's very funny, right? So if I take your two hands, it can be very vivid. And so if I put a rubber hand in front of you, right, and then I stroke the rubber hand, and under the table is your real hand, but you don't see your real hand, you just see the rubber one, right? And it doesn't, it's rubber, it's not your real hand. But if I stroke that hand and you visually see me stroking the rubber hand, and then at the same time I'm simultaneously stroking your other hand with a pen or a feather or whatever, and they're corresponding, so it feels and looks the same. So what you're seeing looks like what you should be feeling. Your brain will actually come to associate that rubber hand as yours, and you will start to almost feel the rubber hand. And so the interesting part of the experiment is at the end, where one of the experimenters comes by with a knife or a hammer and smashes the rubber hand. Very often participants will freak out, right? Like it just freaks them out really, really quickly. And it's like, okay, so you've started to almost associate that limb as part of your body consciousness, is the conclusion here. Okay. Okay. And so what he's saying here is that what you're getting exteroceptive and interoceptive integration, right? So you're getting a rubbing, right? So that's his like interoceptive, right? Because it's like influencing the body sensory neurons or whatever, and then you're getting exteroceptive, so you're seeing and the way manipulated. You're getting an integration of those two things into what's called like proprioceptive prediction, right? So processing of like where is your body, right? And you start to manipulate it so that the rubber hand becomes part of your body, and now you're seeing that these expectations and bottom-up processing are integrating to influence what your current consciousness is. Okay, and so he ultimately says, I predict myself. In other words, I'm predicting where myself is in space and what is influencing, what is interacting with myself, how is it interacting with myself, and I am, right? So my consciousness of the body is a result of, expectations of what's happening to the body and current stimulation. Thank you, Moise. I'll see you later. Okay, so he ultimately thinks that consciousness is a body self must result from predicting the body's state relative to the world. He says, why should we study consciousness? Well, here's a couple reasons why we should study consciousness, and then, basically end here. We should study consciousness, for example, if we want to answer the ethical question, or just the purely question out of interest, is an animal consciousness? Is an animal conscious? For example, an octopus. He cites that an octopus has about half as many neurons as we do, 0.5 billion, right? He actually suggests that there's more neurons in the arms of the octopus than, its like central nervous system. So maybe, there's meaningful conscious systems within the arm of the octopus, like maybe in the central nervous system as well. So, maybe its arms have a very meaningful conscious experience. And that's an important ethical question if we want to talk about, whatever, ethics for animals. at what point is a child meaningfully conscious, right? That's an important question if we want to talk about, like, I don't know, like abortion or whatever laws like that. Um, okay. Clinically, measuring the level of consciousness, again, is important for if you want to determine patient improvements, or, should you pull the plug in a patient that's losing consciousness or has lost it. And then he talks about psychological disorders as disorders of consciousness. So, people who lose their sense of identity and take on a new identity. This is very, like, this kind of condition depends on where someone is, what their culture is. So, in certain Arabic cultures, people who get this condition think that they are Muhammad, the prophet, right? In other traditions, people think they're other famous people, whatever. So this is ultimately a disorder of consciousness. Same thing with psychotic disorders, right? Getting hallucinations. So there's issues in, like, actual perceptual processing, but there can be identity problems and also problems with the perception of body self, right? So I remember learning about patients. They can feel like they almost lose sense of, like, what their body is relative to other things, and, like, it's really amazing and really, really, like, curious to think, like, wow, like, so this woman, she was describing it as, like, she couldn't move, like, she couldn't get up from the chair because she felt she was the chair, and it really was distressing because she felt like she was paralyzed. She couldn't move from the chair. She became part of the chair. She just couldn't move, and this is, like, very odd but interesting, right? Anyways, Seth suggests that it's important to study consciousness to understand what are the mechanisms of disorders of consciousness and how do we treat it, how do we, measure consciousness, and then, base an ethical system off of how do we treat other organisms. Okay. Um, Interestingly, he talks about cortical organoids, right? So these little things you grow in a petri dish, which are just like clumps of brain tissue, right? You just grow these things. He's like, is there a meaningful consciousness to any degree in that little thing, right? And then at what point can we grow a full brain and say that's a meaningful consciousness? And is that ever possible? Is it ever possible to grow a meaningful consciousness out of a brain in a vat, right? He cites a study with a pig, pig brain. So you take dead pigs and you take their brain and they're recently dead, and then you pump some fluid in, and what you find is you have brain dynamics. You have actual brain activity occurring. The researchers gave the brain anesthesia to make sure that it wasn't feeling any pain or whatever, but they were seeing brain activity, and it's suggesting it's like, okay, so maybe it is possible to have a brain in a vat. So maybe the important conclusion here is, like, is it possible to have consciousness without sensory input? And it's a big maybe, right? Brain in a vat. Anyways, another reason to study consciousness, how and at what point will AI become conscious? Seth is suggesting that intelligence and consciousness are distinct, right? He suggests that consciousness is actually more of a product of life itself. It's a necessary product of trying to maintain homeostasis and just trying to perceive the world, operate within it, but also, maintain and perceive the body. And he suggests that if an AI is ever to experience consciousness, it must develop a perception, a consciousness of body, and it must have a meaningful body. Okay. Okay, very close to done. Thank you guys for sticking in. So perception of time, he suggests, is the brain's best guess of the rate of change of perceptual information. He suggests that what's interesting here is you don't have a clock in your brain, right? Like, you don't have, like, just neurons firing every second to give you a perception of time, but rather what you have is this processing of the rate of change of perceptual information, and from that you infer how much time has passed. And he suggests with his VR experiments that you can manipulate the rate of change of visual information in VR, and from this you can both manipulate how a person thinks time is passing in the VR, but you can also manipulate how an AI system trained on this kind of visual information, and then to recognize or to predict how much time has passed. You can also trick the AI system by manipulating the rate of change of this visual information. Okay. Okay. Change blindness. I've talked about it before as this, you don't notice changes in perceptual information, and he suggests that this results from prediction of what is happening, right? So You might just predict it's either such a small and insignificant change that it's not salient and you just don't notice, but it might also be, like just like such a small and subtle change that you think maybe it's just a result of changes in lighting or whatever. Okay, and again, it's just a result of your brain's best guess of what's happening out there in ambiguous stimuli. And so he says, ultimately, a sense of self is a perception. The body, he cites, sorry, I'm so sorry, this is very disorganized, but the body swap illusion. So he uses VR to create a sense of yourself swapping bodies with another. This is actually probably the most interesting experiment he does. So the body swap illusion is you and someone else wear VR, right? And it's similar to the the rubber hand illusion, right? So you're both wearing VR and you're looking at each other, right? And this is like a live stream. You're both looking at each other. Now, if you walk up to that person and shake their hand, what do you think you perceive? You actually get a sense that you are shaking your own hand because you're seeing yourself. And so you think you are shaking your own hand. Now, in higher order regions, you know that's not happening, but you get a weird sense that like it's almost like you're interacting with a clone or something. It's very weird. Okay. So the concept of self may paramount more closely be related to the association to life than IQ, and that's everything. So again, I apologize for how unorganized that was. Anyways, yeah, anything that stood out to you guys? Thank you guys for listening.
Yeah, that was a good presentation. That was nice. The
I'm
only
sorry.
issue.
I'm sorry for the jump. I realized as I was going that was really like.
No, that's all good. Most of
Yeah.
what you said was kind of interesting. I tried to listen all of it. I really did, but I got just 5 minutes
Yeah.
left. Okay.
I think I did a really bad job of explaining it, but ultimately he's citing a lot of experimental designs where you're suggesting that top-down information processing is paramount, right? And top-down information processing is, it's just predictions based on past experiences or even just born-in predictions, right? Like maybe just genetically hardwire predictions or biases in a system that allow the system to interpret ambiguous information. And he suggests that this is just unnecessary, like the sense of consciousness that results from this bidirectional processing, like the sense of consciousness which emerges, it's just a necessary one to this kind of processing. Anyways, I don't know if that makes sense. I don't know if it even makes sense to me saying it's necessary, but that's what I have for you guys. Yeah, it was a good experience learning about this guy and reviewing him. So yeah,
You covered a lot in this
Ethan.
presentation. I was trying to keep up. Like I was trying to think of what you just said, and you move on to the next topic. So
Yeah, was I too fast? Was that the issue? And also
yeah,
kind of scattered.
yeah,
Yeah,
you were way. I think you were too
but
fast.
if
But
you
maybe
like,
not
if
for yourself.
no, I definitely did a horrible job of presenting that. But the ultimate conclusion is that the very important thing, like, okay, I like do you guys know what I mean by sensory stimuli being ambiguous? Like, does anyone have an idea of what I mean by that?
Sensory stimuli being ambiguous. What do you mean?
Yeah, because that was a very important thing that I kept referencing. So what I mean by that is that like sensory information can be represented as a whole data set, right? Because it influences whatever you're sensing it with, right? So if you think of the retina, right, it's a 2D sheet of photoreceptors, right? And what happens is it's taking it's firing in response to different like wavelengths of light and whatever, and you're getting this like crazy data sheet that's being sent to the brain and it's being processed, right? The important thing to note is it's only a two-dimensional surface, but it's creating a three-dimensional perception of the world, right? And then, 4 dimensions across time, but it's creating a three-dimensional perception of space from a two-dimensional input. And so what actually happens is you get basically an infinite number of ways to interpret it, or a very, very large amount of ways to interpret the data. And so what you need is bias to make sense of it, right? So here's an example. There's something called the reverse projection problem or whatever, right? And so this refers to the fact that if I were to draw something, in 2 dimensions, or if I wanted to draw a 3-dimensional object in 2D, or sorry, if I have a 2-dimensional, here's what I mean. If I have a 2-dimensional drawing, there's an infinite number of ways to turn that into a 3-dimensional object. And we know that, right? Like if I take a stick man and then I say, well, this is actually a 3-dimensional object, and then let's say you could rotate it, you'd be like, wow, there is an infinite number of ways to see it. And so if you take any object, right, and you rotate it, like there's an amazing thought where you're like, wow, like, think of your living room table, think of your bedroom. You've never probably seen the exact same point in space. Probably never, right? Because there's so many possible places you could be within it. So you've never probably seen it from the same point in space. You've never seen, maybe your own reflection. Maybe you've never seen your own reflection from the same exact distance from a mirror. Maybe you've never seen your mother's face from this exact same orientation and space from her, right? And the important thing to note is that as you move away from the object, right, the retinal image shrinks, right? And then as you move, the retinal image drastically changes. And so now you have all of these variations of 2-dimensional input, but you can have like nearly an infinite number of ways to interpret it up here, right? Because you're only sensing 2 dimensions, but you're making sense of 3D information. And the answer to it, Seth suggests, and this is a mainstream answer. The answer for how do we make sense of 2-dimensional ambiguous information, well, it's bias, it's expectations. And so some of these biases would be hardwired from birth and genetics, whatever. And then others, you shape these biases over time, right? And as he's saying with his experiments, right? Like for example, in these ones where you have the goggles and you see a face or a house, if I tell you you're going to see a face, you're more likely to see me flash the face. But if I say you're going to see a house, you're less likely to see it, right? Similar detection ones, right? You might detect faster if I tell you what you're going to see, which is, for example, like you might detect the flash of lines more precisely, right? Things like this. So expectation, top-down processing is very important for working with the bottom-up. And the bottom-up is, considered like the basic stuff from the retina upwards into the visual pathway, and then the higher order stuff is like the very, like evolutionarily new stuff, associated with like the outer regions of the brain. Again, like it literally moves in a hierarchy. So the information flows this way, and then it flows back down through the visual system, and you have a bidirectional processing of information. And again, both are very important, right? Because as he cites with optogenetics and TMS stimulation, if you inhibit the top down, the bottom up becomes meaningless. You don't see it. You become blind to things if you just have bottom up. And that's not intuitive, right? Because we normally think, oh, like I'm seeing and I'm just like taking information in and it's just going up to the brain and, I see something. But I can make you functionally blind if I inhibit that top down processing. Now you have, because again, it's so ambiguous that you need bias to process it in a meaningful way. Did that help? Does anyone have to say or? Okay, guys.
I kind of just my bad. That's it for my attention span.
What do you guys think? Is this stuff totally ridiculous? Does it sound abstract and crazy? Like, what is your feedback?
Depends what stuff you're talking about. You kind of just talk about a lot.
Yeah.
First, we were talking about like consciousness, and then I was interested like about the experiment you were talking about because I actually saw the experiment on some video about the fake hand. And I was listening to like the part you were saying earlier. I was just not clear to which concept like you were relating that to. What happens.
one of those interesting experiments too, right, is like creating a phantom limb, right? Do you remember what I was saying about the phantom limb?
Yeah.
These things, like these experiments, are just interesting for their own right, but then once you try to make like conclusions about how the brain is organized and how consciousness is produced, right? But like the experiments are interesting in their own right. So if you anesthetize someone's arm, right, with a local anesthetic, so then they can't feel it. And basically, what the local anesthetic will do is it'll make it so that none of the neurons will fire. It inhibits them, right? And so then you're getting no information being sent up to the spinal cord and brain. You're getting nothing coming, right? But the brain is expecting something because it doesn't know this was anesthetized. So it's expecting something, right? And through those expectations, it changes, right? Like it really manifests the bias, right? And so the top down really takes dominance here in processing the consciousness of body self. And then you get the phantom arm, even though your real arm is slumped to your side because it's anesthetized. It's very interesting. But yeah. Ethan, can I get some feedback? What are you thinking?
Yeah, I mean, like it's definitely like a bit like headier stuff than like than whatever he went over in the one Psych 101 course that I took. But it's interesting how it's like I don't know, like especially this like area of psychology, how like consciousness is still like a very like a very theoretical position still, and it's interesting how the like resources you're reading are like trying to make sense of the like um like more scientific aspects, but also more of like I guess how like a I don't know, like humans using like philosophy would like perceive consciousness. So it's like yeah, so like a really like fascinating subject, I think.
Thank you.
Yeah.
For me, it's like one of the major frontiers, in my opinion. Like in science, it's just one of the coolest frontiers to study. I feel like, like humanity doesn't know at what point it's going to happen, but there might be like some major breakthrough, which will be just like amazing and really cool. Um, and maybe if that major breakthrough, we learn how to make like conscious machines or whatever. There are clinical applications, theoretically and whatever. And again, like he's citing now that you use the TMS or the EEG, right, to measure just like either spontaneous um, uh, waves or activity, or you measure like how responsive is the brain to TMS or whatever, and you can see, or you can get an estimate, you can approximate how conscious is the brain, right? And he's saying like this is currently being used in neurological clinics today, right, to determine how conscious is the patient. Are they becoming more conscious? And we have hope that the person will exit a coma or whatever, right? Yeah. Simon, can I ask you for any feedback?
Yeah, I definitely found it really interesting, Aidan. Like I would agree with Ethan, like they're definitely more on the heavier side, but when you let it sink in for a little bit, I think you start to see some cool general themes emerge. Like I think it's cool to think about how when like what is consciousness and can other organisms or just a brain be conscious, and then how that affects the ethics of an experiment. Just like it makes you think about a lot of like there are a lot of connections to other things in life too through it.
Yeah, like, yeah, I um the interesting thing for me is like, which often like gets brushed over, but like, so Anil Seth is he's a proponent of the information integration theory. Like he is he like supports it and he cites it and whatever, and he's done work in that line, right? I believe. Um, and so I don't know if anyone was here. Maybe Siddharth was here. The like my first presentation where I explained or at least I explained like the first half or most of the information integration theory, or at least like the general concept of what it is. It's very difficult to read, honestly, like this kind of stuff. But basically, it's a theory quantifying how conscious a system is, right? Based on like how like again, like information being like, what is information in any case, right? What is information? It's one state out of a number of potentials, right? And so as the number of potentials increases, right, there's more information. And as that information, so as a state is more dependent, like as the manifestation of a state, it becomes integrated. In other words, more dependent on the manifestation of other states, integrated information changes. Like that's more integrated information. So the more interdependent states of manifestation or information is, the more interdependent information is, the more integrated it is, right? And as the more states are emerging out of more potential states, you're getting more information, right? So in summary, this is integrated information of anything. That's objective into information integration to describe reality, right? And the information integration theory is essentially saying, okay, consciousness can also be described in terms of information, right? So it's described in terms of an amount of information and an integration of information. And Tononi, information integration theory is suggesting that consciousness is an integration of information, at least in quantity, right? And then how you get the contents of consciousness and all the different specifics, he has no idea really, I believe, to actually, how do you quantify, how differences in information results in consciousness in the mind. But he says that we can at least quantify how conscious a system is based on its integration of information. And so in the brain, integration of information means patterns of neural firing, right? So that's the amount of information. And you have basically two in any one neuron, firing, not firing. And that occurs across time, right? And then those neurons are integrated through synapses with a bunch of other neurons. And so then the firing of neurons influences the firing of others. And again, remember, Anil Seth is, and again, this is pretty standard, but like there's a bidirectional processing here, right? So one neuron will influence the other, and that neuron will influence it back. And so what Tononi suggests is he suggests that any system which has this bidirectional causal power, any system which has bidirectional causal power throughout every one of its parts, that's a full conscious system. Like every part of that is conscious. It belongs to the conscious system. Any part that's like attached to it and doesn't have bidirectional causal power, that is not a part of the conscious system. So in a human, you can think of the eyeballs, right? They send information this way. Nothing comes back to the eyeballs, right? And so he explains that this is how the retina is unconscious, right? But the parts of the visual pathway which are bidirectional, he suggests, that's all a conscious system, whatever. And he suggests that any part of our brain which is conscious has this bidirectional causal power and integration. And remember, like the average neuron has 10,000 synapses. Some neurons more, some less, right? And sure, it varies a bit, but now you get an idea, like these networks can become quite large, right? Anyways, so that's information integration theory. And what I find the interesting part, right, is like what I find often undiscussed, right, is like, what is it like to be a system of like maybe 10 integrated neurons, right? So, Tononi makes sense of the cerebellum, where you can have like 60 to 80% of your neurons being unconscious, right? Like the cerebellum as a system, right, which is it's like this little clump of tissue in the back of your brain here, if anyone's familiar with it. Very dense, has a lot of neurons. It's like just little in the back, and then you have the rest of your brain. And this thing, just in the back, has got like 60 to 80% of your neurons unconscious, right? Like people lose these things, and they can have motor impairments and whatever, but they're still conscious. Like they seem like almost unimpaired in consciousness. What I find interesting, right, is that Tononi explains this as just, they're like columns. So they're not like these highly integrated networks. You can almost break it down into just a bunch of different processing units, a bunch of different brains, if you will. And so to me, that suggests that maybe these are like, millions and millions of conscious systems, maybe. Or, tens of thousands, hundreds of thousands, little systems. Maybe that sounds crazy. What do you guys, anything standing out, guys? I'll try to better organize my presentations moving forward. Sound good?
Yeah.
make them more digestible.
Yep.
Because
Yes.
that was understandable to anyone, because that was just craziness.